So outcome of the previous lecture is so the following. So lambda k is integral, and theta is positive. Then I have functions fk going from db coh a lambda theta v to db coh a lambda theta v plus epsilon k, and I have ek which preserve the categories supported on the zero fiber of the morphism phi, and under CC giving fk and ek. And now I'm going to deal, so now I want arbitrary beta, well, with beta dot lambda being integer and theta. And I want similar functions. Good news is that this construction takes this theorem as a black box. You don't need to know how it works. And the idea is the following. So just by definition, so beta is the real root. So there is a simple root alpha k and an element sigma in the Weyl group of Q, which is the same as the Weyl group of the corresponding Kac-Moody algebra, such that sigma beta is alpha k. So real roots by definition are those which can be conjugated to simple roots under Weyl group elements. Okay? So idea is to produce WQ action by isomorphisms of few varieties and the quantization with correct behavior, and I will explain what this means, on quantization parameters and dimensions. Before I'm going to construct this action, so what will I do with this action? Well, I will have like some isomorphisms, and I will just transport my functions using these isomorphisms. So essentially, I'm not producing any new functions. I'm just using existing ones. And before we are going to discuss this, I'm going to produce for you an example that we have already seen. When I say example, I mean that the Q will be such. And then I have, well, let's say theta is positive, then m theta VW is going to be T star of Grassmannian of VW. This is Grassmannian of V-dimensional subspaces inside of W-dimensional space. But it's also the Grassmannian of W minus V-dimensional quotients of the same space, right? That's the same thing. And when we speak about quotients, we realize this guy as m minus theta W minus V W. So remember, this was the same Grassmannian. We had this example in the first lecture. So the same cotangent bundle to the same Grassmannian. And that's an example of a Weyl group action by isomorphisms. So here theta gets reflected. And V gets reflected. You will tell me that that's not a reflection, but if you look at the corresponding weights, then on the weights, this just interchanges nu and negative nu. And nu, in this case, is just W minus 2V. Okay? So that's an example of the action by isomorphisms that I have in mind. And the Weyl group here obviously is just Z2. So now so the plan is first I'm going to produce Weyl group action in the classical case, meaning on the usual Q varieties. Then I will do the same in the quantum case, meaning the action by isomorphisms on quantizations. And then I will construct of functors f beta and e beta. Okay? So that's what I'm going to do. All right. So we assume, so part one, we assume Q is without loops. Then the Weyl group of Q is generated by elements. Is generated by elements Sk, K in Q0, subject to the relations like Sk squared equal to 1 and Sk, Sl, and so on, MKL times. This is the number of arrows between K and L regardless of orientation, plus 2, equal to SL, SK, and so on, same number of times. Okay? This is a Weyl group. And I want to produce two actions.
What do you mean by SL, SK, and how that?
Well, I mean, they repeat. So here I will have SK, SL, and so on.
Ah, okay, yeah.
So I will produce a linear action on the space which I will denote by CQ0. And this is a home for elements called theta and for elements called lambda. These are stability conditions, and these are levels of the moment map, either classical or quantum. And also affine action on CQ0 dual. This is home for elements called V, dimension vectors. And the action is, so you should think that this is secretly a Cartan of my Kac-Moody algebra, and this is a dual of Cartan. But yeah, here the action will be shifted, as we've already seen. So the formulas are, so for lambda in CQ0, Sk applied to Sk lambda is going to be given as follows. So the k's component is going to be minus lambda k, and other components are going to be given by lambda L plus MKL. Oh, that's bad. MKL minus 2 lambda K. So just the number of arrows between K and L. Okay, that's more or less usual formula. And action on CQ0 star is given by Sk applied to V k is Wk plus the sum over all A such that HA is equal to K or TA equal to K. V, oh, that's a better way to write it. Okay, so the sum over all A with H of A equal to K V T of A plus the sum over all A such that T of A is equal to A, T of A equal to K, VHA minus VK. Or, in the notation that I used before, it's WK tilde minus VK. And what this action does on the level of the corresponding weights nu is just the usual linear action. So nu goes to what we denote by Sk nu usually. So I just conjugate the weight in my G module by the Weil group element. That's the only thing that happens here. And in the special case that I've considered on top, we see that those were the action of the reflection in SL2. Okay? Now there is a theorem due to Maffei and something very similar was also obtained by Lustig and by Nakajima. Theorem is the following. So if lambda k is different from 0 or theta k is different from 0, then m theta lambda v is isomorphic to m sk theta sk lambda sk dot v. Something that we have already seen in the example, right? So if you specialize to this example here, this is what the theorem says. So you see that the isomorphism is very stupid. It's just two ways to realize the same variety as in a Kojima-Q variety. So basically those isomorphisms is just, they just rename these parameters. That's all that they do. And so idea of proof, don't be surprised, it's still reduction in stages. So the reduction in stages tells us that m theta k v 0, well, okay, 0, this we know this for 0, is isomorphic to m as k theta k, which is just minus theta k, 0, sk dot v. So note that the action of sk here doesn't change.
What is the deeper?
Sorry, I forgot to say this. So all other components remain unchanged here. So we have this isomorphism, and in fact, so this can be upgraded to m lambda k theta k v to m minus lambda k minus theta k sk dot v. So in this case, we will just get the same twisted cotangent bundle on the Grassmannian times the same vector space T star of R underline. And then what you need to check, so we need to check that under these isomorphisms moment maps mu underline and stability condition theta underline are transformed as needed. What does it mean as needed? Well, in order to produce required isomorphism here. So the moment map is defined up to adding a character, and lambda minus sk lambda will be a character of my algebra. So we need to show that under this identification the moment map shifts like this, and it's relatively standard. So if you've seen like reflection functors for deformed reprojective algebras, which is more classical topic in representation theory, then this is how reflection functors act on these lambdas, and that's some computation. And the story about stability conditions is more difficult. So Maffei's paper contains some very nasty invariant theoretic, very nasty, I don't know, invariant theoretic computations which ensure that stability conditions behave as needed. In any case, so that's how it works. And now, so what do I need to say here? All right. Now what about, how about general sigma in WQ. Well, I can of course decompose this sigma into simple reflections. So I take some reduced decompositions. This one is I1. And then I can start applying the simple reflections and corresponding isomorphisms to my data, to dimension vectors, stability conditions, and levels. And I may not be able to, you see, in my theorem I have two conditions. I have conditions that lambda k is equal to 0, and in a Q variety I cannot modify this lambda, but I can modify theta. I can modify theta inside of its chamber. Can modify theta inside of its chamber.
You need to check Bray relation.
Yeah. So if you want to check that this gives an action of a Weyl group, you need to check Bray relations, but this is due to Maffei. So he did that. And I will not care about Bray relations much. It will be enough for me to produce at least one isomorphism per every sigma. So inside of its chamber, so that sigma I1 is different from 0 as I1 sigma I2 is different from 0, and so on. So this I just need to remove some finitely many hyperplanes from the chamber. Obviously something still remains after I'm done. And this produces an isomorphism M lambda theta V isomorphic to M sigma lambda sigma theta sigma dot V. And it's so if you want to practice with this, you could try to take some flag variety of type A and see what's going on. So there is the most obvious realization of a flag variety, like just a chain of subspaces. But here you will be dealing with something like some of them are subs, some of them are quotients, something like this. All right, so this was the classical story. Now let me proceed to the quantum story. So now part 2, I want to quantize, so goal, quantize Maffei's isomorphisms. So I want to leave them. So I want to leave this isomorphism 1 to an isomorphism of A theta lambda V with A sigma theta something. Well, let me write sigma dot lambda sigma dot. And so my difficulty here is that this is not the same. So sigma dot lambda will not be the same as sigma lambda. And the reason is that when I do the classical computation, I have a distinguished moment map, just quadratic one, homogeneous one. When I do quantum computation, I don't have a distinguished moment map. Quantum comoment map in particular depends on the orientation, right? But I have a symmetrized quantum comoment map. So recall that I have phi sim of xi is 1/2 xi r plus xi r dual, which can be also written as xi sub r plus 1/2 of the trace in R of Xi. Now this is a canonical one, and when I use a canonical one, the action on parameters becomes linear. So with phi sim, I get linear action on quantization parameters well as before. So the result here can be stated as follows. So theorem prime, well, I mean, oh, I don't know. Is that the shifts, sim here means that I use the symmetrized quantum moment map, a sim theta lambda v is isomorphic to a sim sigma theta sigma lambda sigma dot v. And if I want to remove sim here, I will need to shift a parameter by some number, but the number will by some element, but the element will be integral. So it's equivalent to say that a lambda theta v is equivalent to a sigma theta sigma lambda plus something integral sigma dot v. And I don't care about integral shifts because the categories of modules don't depend on these shifts. So with this isomorphism, now we can do the following. I think that I will need, okay. Now let's proceed to part number 3, where we finally construct the functors. And so I start with some beta. I pick sigma such that sigma beta is a simple root. Now beta was a root for a lambda, meaning that beta dot lambda is an integer. But you see, this pairing is invariant under the Weyl group action because these two Weyl group actions are dual to one another. So this dot pairing, so dot from CQ0 times CQ0 star to C is WQ invariant. Because essentially what's going on is that I have two dual actions of W on H and on H dual. And this is a natural pairing. So it follows that alpha k paired with sigma lambda is an integer. And what is alpha k paired with sigma lambda? This is just k's coordinate. Alpha k is just coordinate vector. So this is just sigma lambda k. And so now I have a quantization parameter where k's coordinate is integral. And because of this, so let me maybe, well, it's sigma. Okay, so now I will need this entire blackboard. So I have this quantization parameter, sigma dot lambda. And I have theta plus stability condition with positive entries. Under this assumption, I have Webster's functors. I have functor fk, which will go from dB a theta plus sigma dot lambda sigma dot v. I write Koch here, so let me do this. Okay, which goes to dB Koch a theta plus sigma dot lambda sigma dot v plus epsilon k. Okay, so I have constructed such a functor before. So here I am precisely in the setting of this construction because of this.
Is the fk?
Yep, that's an of k. Now these categories are equivalent via derived global sections to dB a sigma dot lambda sigma dot v modules and similarly in the bottom. Okay, so I get a functor between these categories. So what do I need to do now? Now, well, I want to change the stability condition to this one. And I can do this using localization functors. dB Koch a sigma dot lambda sigma theta sigma dot v Okay, so I have a functor between these categories, and finally these categories are equivalent. So this is derived localization. So here I had R gamma for theta plus. Here I have derived localization for sigma theta. And finally, I have a very stupid equivalence of derived categories, which is just given by twisting with an isomorphism coming from sigma inverse. So here sigma star, well, sigma is an isomorphism of a lambda theta v to a sigma dot lambda sigma theta sigma dot v, and sigma star is corresponding push forward.
So this is totally parallel to geometric reflection factors in simple. So globalize and then localize in different places.
Yep. And then do this change.
And this change is necessary just to return to the original
Yep.
stability.
To original dimension vectors and roots.
Dimension vector.
Okay, so what do we get? We have dB Koch A lambda theta V for this guy. And in the second line we have dB Koch still A lambda theta V plus what? So plus sigma minus 1 of epsilon k. Epsilon k is the same root as alpha k. So epsilon k is just another name for alpha k. And sigma minus 1, alpha k is beta. V plus epsilon, V plus beta. Okay?
Possibly a typo second column bottom row. This is the same as what's written above it.
You forgot the answer.
Yep. Thank you. So what happens? So we start with functors which are defined for one particular stability condition. And this was important in the construction. But then we can switch the stability condition by doing these equivalences. And once we switch them, well, we can now define a functor between these categories. Just by using this kind of trivial isomorphism, which just don't change the algebra, but change the way how we present it. All right. So now what do we need to check? So outcome we have functors f beta going from dB Koch A lambda theta V to dB Koch A lambda theta V plus beta. And we have E beta, which goes in the opposite direction. What do we want from our functors? Well, we want them, properties that we need, we want them to preserve categories of complexes supported on phi minus 1 of 0. This we want them to have. And this is relatively easy. So first of all, the functors, well, I mean this, here I don't speak about phi minus 1 of 0, I speak about finite dimensional homology. And so all these functors, they kind of, so these functors will map category corresponding to phi minus 1 of 0 to category with finite dimensional homologies. And these functors will map it back. This we have discussed. So I can write it in this form. So L log sigma theta composition with R gamma theta plus preserve such subcategory. So just from compatibility of supports with pullbacks and push forwards. And now I have this push forward by isomorphisms. And they also preserve, so preserve these subcategories. Because sigma maps phi v minus 1 of 0 to phi sigma v minus 1 of 0. And this property just follows because this Lagrangian subvariety is just determined uniquely from the Q variety. So let me elaborate on this. So this follows from the following observation. So what is phi? Phi, if you remember, phi v, was a morphism, a canonical morphism from m theta v to spectrum of regular functions on m theta v. So that was the construction. And obviously, if you're applying a automorphism of this variety, so nothing is going to change. So automorphism will map this guy to the similar morphism. So the variety carries an action of a one-dimensional torus. The action contracts this guy to a single point. The morphism sigma is equivariant. And so you just recover phi v entirely in terms of the variety and the action. And since the isomorphisms preserve the variety and preserve the action, they are forced to preserve zero fibers. So that's the basic idea. So this is something which is easy to check, but now we also want compatibility with Nakajima operators. So informally, I can write it like Cc of f beta should be plus or minus f beta. And this is considerably harder than part 1. So for this you need to establish two claims. The first claim is that this L log sigma theta in position with R gamma theta plus preserves characteristic cycles. And this was already mentioned. So Hasse, in one of his talks, mentioned that the characteristic cycle map is well defined. So meaning that the characteristic cycle map is independent of the stability condition. So this functor changes the stability condition, and the claim is that it doesn't change the characteristic cycle of your complex. And this is not trivial. So I'm not going to elaborate on the argument. But now another technical statement that you need is the following. So now, what does sigma star? So how sigma star affects characteristic cycles? That's a more interesting question, and I'm going to spend the last maybe 5 minutes in this lecture discussing this question. Okay? So sigma is an isomorphism of m theta v with m sigma theta, sigma dot v. And an isomorphism of varieties gives you an isomorphism of homologies, in particular of middle homologies. H middle m theta v to H middle m sigma theta sigma dot v. But now we've made a remark that this space here is independent of theta in a canonical way. So the homologies of all Q varieties are identified. So what does it give me? It gives me an action of the Weil group on the sum of all middle homologies, sum over V, H middle, M whatever V, and this is just the space L omega. That's a module over my Lie algebra, integrable module. Now this looks a little bit surprising, because if you have a module over, say, semi-simple Lie algebra, the while group of that semi-simple Lie algebra is not supposed to act there honestly. But it's supposed to act on it by projective transformations. So the problem is that if you have a while group of a semi-simple Lie algebra is some subquotient inside of the corresponding algebraic group. And so you first need to leave the while group to the algebraic group, and then you can act. But it will not be a linear action. It will be action of where compositions just differ by signs on corresponding on suitable signs, one for each weight space or something like that. But in any case, so this gives rise to a projective action of WQ on L omega. Okay? So we still have some kind of action coming from the representation of a Kac-Moody algebra. And the thing to be checked is that the two actions, so claim two actions coincide up to signs, which is a reasonable thing to expect, because this action is also kind of defined only up to multiplying by plus or minus 1 in various places. All right. And from here, you actually deduce you can deduce that when you apply sigma star to f beta,
From the clay.
yeah, so sigma star f beta sigma star minus 1 is going to be plus or minus fi. And this is what is needed. This completes checking the property. So property 2. And a couple of words about how this is proved. Well, we don't have any normal proof of this fact somehow. It's something which is unpleasant to check. There is a way to reduce it to the Grassmannian case, but we haven't checked this even in the Grassmannian case, because we have another way to check it, which is rather indirect. And the way how this is checked is by relating this kind of functor to a functor coming from a categorical Kac-Moody action, which is called Ricard functor, Ricard complex, which is also necessary for some other purposes. But I'm not going to elaborate on that. I'm just going to tell you what's going to happen after this long break. So after lunch, we will discuss functors of the form like that. So L log theta prime composition with R gamma theta. So what these functors do, they change the stability condition, and they are called wall crossing functors. The reason why we are going to discuss the functors is that they provide tools to prove the inclusion in the other direction, to prove what is called upper bound. And basically, the way how these functors are studied, if Professor Arkhipov is interested. So the basic idea is that we need to cross a certain number of walls. And so it's reasonable to start with functors crossing a single wall and see how they behave. And this behavior of this functor drastically behaves on what kind of wall is that. So if the wall is defined by a real root, then functors are relatively easy, because kind of the only thing that, I mean, you can reduce them to the case of T star of Grassmannian. When the functor crosses the affine wall for affine quivers, it's now a different behavior and it's more complicated. But we don't know what happens for wild quivers. Somehow that's a problem here.
So that's exactly the place where you use the type.
That's one of the places where we use type of a quiver. Another place is that for affine quivers, we have only one imaginary wall. For wild quivers, we have a whole bunch of imaginary walls. Each of them presents a difficulty, and the fact that there are several of them presents some additional difficulties.
So in principle, what can you follow from this categorical 2 and 5 Kaz-Moody?
So categorical Kaz-Moody action takes care of wall crossing functors through real walls, and it doesn't know anything about wall crossing functors through the affine wall, because it's somehow, I mean, you don't have any root, any kind of Kaz-Moody generators for the affine, for this weight space of weight delta or of multiples of delta. There is a speculation that categorical structure which should take care of these functors should have to do with categorical Heisenberg action, but this was never established. One can further speculate that when you need to do more general cases, you need to use some Youngians of Maulik and Okounkov, but I mean this is we don't have I mean, so we have some relatively well-defined speculation for the case of the wall Kerr delta here, of the affine wall, but for more general walls we don't even have any speculation. All right. Yeah, so I finished.
Yep.